So let's see if we can work this through. In the case of gamma equals 1 and probability of left is a half and probability of right is a half. It turns out it will be nice to solve for the value function. So let's have three variables that represent the value function, one from each of those states. From the z state, what happens? Well, with probability a half, we go to the right, which ends up giving us an immediate reward of 0, and then we get a discounted value of being back in z.
Mm-hmm.
Or with half probability, we go to the left, and we get our reward of 1, and we're done. So z is 2/3.
Yeah, it's just boring old algebra. Oh, I see. You magically put 1/2 in where gamma used to be because gamma is 1/2. That makes sense. Okay, fair enough.
I thought that would make things easier. All right, so z is 2/3, and let's work out x and y.
Okay, so I guess you will do a similar thing.
Yeah, so the value at x, from x with probably a half, we go to the left, which gets us a 0 reward and then a discounted value of being back in x. Or with probably a half, we get no reward and then we have a discounted value of being in y.
Mm-hmm.
Meanwhile, y, the value from y, is, well, with probably a half, we get the discounted value of being in x. And with probability a half, we get a value of 1, and we're done.
So that's two equations and two unknowns.
Yes, linear equations.
It's even better.
So convenient.
Cool.
And some normal algebra-ish kind of things later. I have x is 2/11 and y is 6/11. Better to be in y. So when we average our expected reward, our discounted expected reward from each of these possible starting states, we get a third of this and a third of that and a third of that, or 0.4646 as our value for taking this stochastic policy.
That's not even 50-50. Ha!
Okay, and we said that we could do better. So we said we could do better by choosing probability of left to be a third and probability of right being 2/3, right?
Yeah.
All right, so let's see if that actually gives us a better number.
Okay.
So we need to work out what the value of z is in this case where we're going 2/3, 1/3. So once we solve through for z, we find out that z is a half. Before, z was 2/3. And so we actually are doing worse in this state because we're spending more of our time bashing against the wall to the right.
Yeah, grad school.
And we're going to write down what happens from these other two states. So the value at x, which simplifies to 5x equals 2y. And the value at y is, again, we're going to go to the left 1/3 of the time, getting us the value at x. And we're going to go to the right 2/3 of the time, getting us our value of 1. All right, so once we solve all that through, we get y is 5/7 and x is 2/7. And so when we average these three values out, we actually get a half, which is a little surprising to me that the 7s kind of cancel out. But a half is bigger than 0.464646, so we actually have a better policy.
Right, and coincidentally, it does give us 50-50.
What do you mean it gives us 50-50?
Well, you said you wanted to do better than 50-50, 0.5. That's 50-50.
No. The 50-50 policy, which gets us 0.464646, we did better than that policy by trying a different policy that actually gets 0.5.
I know, Michael. I was using wordplay.
Ah, brilliant.
Thank you. So I suppose using all of that algebra, we could actually figure out what the optimal numbers are if they aren't 1/3, 2/3. Maybe they are, just by replacing all the 1/3 and the 2/3 with p and 1 minus p. And we'd figure out what p is.
Yeah.
And I'm sure that would be a wonderful exercise for the students to do.
All right, so we'll leave it for that then.
Excellent.